Hi, welcome to the webinar. We'll wait for another 2 to 3 minutes to allow more attendees to join in, and we'll start soon. Thank you. I hope everybody's safe within the confines of their home, as approximately more than 2 billion people today are under lockdown of the terrible tragedy that's unfolding in the world. What we would like to do is, for people who have missed some of the portions of the webinars before, since this is the last webinar we are doing on 5-axis, I would like to capture or recap what we have done in the past webinars. I also am aware of my last webinar where we had some issues of the audio, and that's why I'm going to repeat some of the things that I did in the last webinar, especially the circle tools, circle end mills, the barrel tools, and also the multi-axis roughing. And I will close my session today by touching upon two very important subjects. One is multi-axis drilling, and the other one is the singularity or pole handling inside SolidCAM. How the last screen of SolidCAM, which is a mystery to many of us working with the 5-axis, what that screen basically means and what it does is what we are going to see today in our webinar. So I'm going to touch upon the earlier parts, the earlier webinars that I did, right from part 1 to part 4, and we will just quickly run through them. So today's webinar is a bit lengthier one than the ones before, so we'll have to have some patience in bearing up with me till we reach to the last two subjects what I discussed just today. Right, so in the very first webinar, we saw how this part could be machined. Basically, I used the drag and drop templates that are there in SolidCAM. I basically use what is there with me in the templates here. And sorry, let me pull the window out here. So I've got the templates in here, and I could just drag any of the, for example, the facing templates, and just drag it and drop it on the face out here. And that's how my the calculation used to happen. Okay, we don't want that calculation now. So we have seen how each of this operation was generated using the template method. For example, the first facing out here again was generated using a template. A second facing, just drag and dropped it on the face. and the machining happens. So not only does the machining happen when you're using a drag and drop template on multiple sides, but it also ends up generating the coordinate system when it is creating the operation. So you don't have to create the coordinate system again and again. You just need to just pick, drag, and just drop it on the face, and the coordinate system will be automatically created normal to that face. So this is how we did. What we missed, maybe in the other part I will show you, was one of the operations, and I'll come to that. What we also saw was our new roughing strategy, which is the turbo roughing, where I showed you several things. For example, takes into account the undercut stock. It doesn't go all the way down because it's a straight wall. It doesn't go, it just stops exactly where the stock ends, because my stock has got this shape here. And because it has this shape, it stops exactly at the right place. Takes into account the undercut situation of the stock. You can define, if I go into my roughing window, you can see that you can define multiple offsets for different group of surfaces. So you can have 1 millimeter for one offset, you can have 0.5 for another group of surface, you can have 0 for some group of surfaces, and so on. You can have different offsets. This is one of the highlights of turbo roughing. Also, within the software, we have got the adaptive feed control. So basically, when you're using an inserter type cutter and when you're going into the corner, you would not like to go with 100% feed rate, especially when you're going into the corners. You would like to drop the feed rates. So you can specify what is the minimum feed rate that you would like to go down, and the software will take into account that and keep varying the feed rate based on the engagement it is finding with the part. Passes were all simple. We have Z top, Z bottom, the cut tolerance, and then we have the adaptive step down. In the adaptive step down, what we have, the specialty is you can define range. Okay, you can define user cut levels, and you can add, and you can say from minus 9.5 to minus 50, I would like a step down of 3. And if I add the next one, it'll automatically take the minus 50 next one. And I'll say minus 50 to minus 100. I would like a step down of 2 millimeters. And if I add another step down here from minus 100 to minus 125, I would like the step down to go down to 1 millimeter. Okay, so you can have, or you can define the range of step down between certain Z levels, and that's how you can get different depth of cuts at different Z levels. Another highlights with SolidCAM Turbo HSR. Okay, so this is one of the highlights of Turbo HSR. Apart from the adaptive feed rate, the different surface offsets that you can provide with to the geometry. So a lot of things are new inside Turbo HSR. Then we moved on to the rest roughing functionality of Turbo HSR, where it takes into account, for example, I can go at an angle with a completely different coordinate system, and only that region or where the material is remaining will be taken into account, and we will work only on in that area. So you can see that there was a lot of material remaining in this because it's an undercut for me, and because of that undercut, a lot of material was left out, and I used the rest rough functionality at an angle, and it detected exactly the stock remaining and machined only that area where the stock was remaining. So that's the turbo rest rough. Then we moved on to the 5-axis operations. Again, we used the drag and drop template where I generated the swarfing operation to machine this particular face here. Okay, so I said instead of one cuts, provide multiple amount of cuts. So this entire surface was machined, and also the bottom. This is a 5-axis operation that we have created, and you can see that I used a ramping method because there's a lot of material remaining on the pocket. We did not do any kind of semi-finishing. Being a soft material like aluminum, we directly went for finishing it. So I used a simple trick inside the 5-axis operation where entry can be changed from a simple tangential entry to a helical entry. Okay, so you just need to define the angle and the height of the helix, and it will create a helix which mimics the helical entry in 3-axis. Similarly, I used the generic 5-axis here to machine the side of the pocket. So if I show you the simulation simply on a HostCAD method, HostCAD type, you can see that it's just machining the side wall completely in 5-axis. Even in 5-axis operations, I can define zones. I can define zones where I need to define or reduce my feed rate or increase my feed rate. Okay, these are called as feed zones. For example, I can edit this operation, go to the tool, and in the feed control zone, I can apply the minimum and maximum feed rates based on the areas that what we are working with, and the feed rates will automatically change when it goes into that particular area. Right. Once that was done, we moved again into our sidewall finishing, basically using the same generic 5-axis. Okay, these are all simple templates that I've stored, and multiple cuts. What are the side faces that I selected? These are the 3 side faces that I selected. I used a ball nose tool in this case and just created 3 passes. Based on these 3 passes, the wall was completely machined. Right. We also did some other work, and that was using the barrel tool or the oval form tool. We machined the internal surface here. Okay, so if I run the simulation, this is how it's going to look like. I'm going to touch the barrel tool again today on those 2 exercises that I showed, so that you know exactly what we can handle, what kind of tools we handle, how we handle the tilt and stuff like that. So I'm going to touch upon those areas again. So you can see that we are using the large radius of the oval form tool. The advantage here with the barrel tool is that using a large radius, you can actually have a bigger step down and yet achieve the same scallop that you would achieve with a very fine step down using a ball nose tool. So number one, the main advantages is that your surface quality is much better than what you would get with a ball nose tool. Number two, your time to machine that particular surface comes down dramatically because you're going with a step down that is either 3 to 4 times more than what you would generally take with a ball nose end mill. And that's all because of the large radius that it has got on the side. So we use the large radius to cut the surface. All right. We also have seen another very important thing in this part, and that would what we call as the common direction. What is a common direction basically? A common direction is pretty simple. We actually generate the toolpath in 5-axis, and we have provided some surfaces here. For example, this 3 surfaces were provided as our check surfaces. And the moment these 3 surfaces are provided as check surfaces and we touch upon this button here, I have to show you in the toolpath. If I go into the tool axis control, under advanced, you have got the maintain tool common direction, tool axis common direction. So the moment I select this, what SolidCAM will try and do is it will try and find the best possible position in which it can lock the axis, the rotary axis basically, the swivel and the rotary, and machine that surface in just plain 3-axis. Okay, so if you now look, it was basically a 5-axis operation, but if I run the simulation, you will see that it's a simple 3-axis operation. Okay, Let's go again here and run the simulation. You can see that it's a simple 3-axis toolpath. It has found the best possible orientation, locked the swivel and the rotary, and just running it simply in 3-axis. You can use this wonderful technology for most of your machining where it is possible. Just lock it and machine in 3-axis. The advantage here is that when you go into 3-axis machining, it's very robust, much more robust than going in 5-axis. So you are actually locking it and using only the 3-axis. So it will give you, number one, a much better surface quality. You can still use the small tool, the small length of the tool, and machine those areas which are not basically possible in 3-axis. Okay, so it will just lock and machine it. And the toolpath quality is also pretty good. You can look at the quality of the toolpath. Oops, sorry. Just wait. In the event it doesn't, then we'll have to restart. Not a problem. Let's not waste time. Right. We'll now move on to the second part that, or the second part of the webinar that we did, the part 2 webinar, which was another very interesting part that we took. Let's open the part. It was basically a closed impeller, a part that looks relatively easy, but it's very, very difficult to compute as far as the toolpath calculations go or toolpath generations go. They're not simple paths. So what we also saw here was a completely different approach for tilting. As far as the final part is concerned, because what we did on that day was simply the 5-axis, but what we have done here is I have created several 3+2 toolpaths to first remove or scoop out the maximum material, and then we used the Sim 5-axis, the generic 5-axis engine, to finish the part. What I did not show you the other day was a new operation inside SolidCAM, and this is called as the undercut milling. It simply uses the entire surfaces that is there as the input geometry, basically converts it into a mesh, and then uses either a lollipop tool or a slot mill to machine simply in constant Z, even those areas that are not possible in the regular constant Z machining. So it allows you to machine undercuts. For example, if you look at this surface here, the surface here on this side, this portion is completely an undercut. So here, this portion is completely an undercut. So if I edit this part, okay, and if I go to evaluate and go into the draft angle analysis and select this, you can see that this area here is an undercut. Okay, so it's having a nice angle here. Even if it starts from top, it has an angle of almost minus 13 degrees. So it's a pretty deep undercut that we have. So what the 3-axis constant undercut milling does is basically generates constant Z machining, taking into account the cutting part and also the shank and holder. Okay, it takes into account, and it can machine as much as possible. In fact, a very good idea to do this was to use a slot and mill, and actually you could have gone all the way down as much as possible on this side and then machine the other side, but that's for a different day. We only were more concerned to finish up to this portion or slightly below that, and that's why I use the 3-axis undercut. It's simple. The operation is very, very simple. All it asks you is the target, how much is the offset that we'd like to keep, what is the tool, and here we can use the simple lollipop cutters. Okay, so we have the lollipop tool here. So we use the lollipop tool. It's asking me from the levels, basically the constraint boundaries, if I have to specify, passes, basically the Z top and Z bottom, the step down, the method you would like to cut, one way or zigzag, and that's it. Once that is defined, it just generates this pretty nice looking toolpath, which is completely taking into account the undercuts of the surfaces, and it will machine only those things that are possible with the current geometry of the tool, including the cutting area and the shank. Right, once that was done, we moved into the semi-finishing and finishing of the cyan colored surfaces that are here. So what we did was we defined two groups of surfaces. So if I switch off the solid body, so we created two groups of surfaces here. We did also some surfacing work in that webinar. So we have the group we call as the upper surfaces. So we created this group, and we also have created a group called as a lower group of surfaces, so that we have two groups, and both the groups obviously are overlapping, so that the tool paths that we create also will overlap in such a way that it doesn't leave any mark where it is stopping. Okay, there is some portion of an overlap from one surface to the other. So we created these two surfaces here, and what we also did was we saw how completely different tilt curves can be created, how the tilting can be handled by tilt curves. So we also saw the function of creating this particular tilt curve, which will be used for machining the cyan colored surfaces from the top side. And then we also have another tilt curve here, which is the bottom tilt curve. And this is how we generated the bottom tilt curve for surfaces or for area that will be machined from this side. And what we did was we used the generic 5-axis, and we used the group of surfaces which I just showed you, the top surface and the bottom surface. The tool here was again a lollipop tool, and the tool axis we used in this case was tilted through curve. And if I show you the curve, this is how my curve looks like. The pink colored is the curve that we use, and the sub option that we used inside the tilt curve was start to end. Okay, another thing that we did was most of the, or by default, SolidCAM always does the tip calculation, or the calculation method is always by the tip. But in this case, the tip doesn't give a great result because of the complexity of the surface. So we have got a very nice option in tool axis control where we calculated the tool contact point as the center of the tool and not as the tip of the tool. And then we use the gouge check, because the moment I say center of the tool, I'm actually going to get the tool path exactly lying on the surface, which is basically colliding or creating collisions. In order to avoid the collisions, what I did was I created the tool path. So if I actually go into my drawing, okay, let me capture this area. So what I did was, let me change the color. Okay, let's go with blue. So I created the tool path exactly on the surface, okay, which was lying on the surface using the center method. And then if I go into my SolidCAM gouge check method, I used a function called as retract tool to cut center. Okay, in that case, I've just used the tooltip to be checked. So what I basically told SolidCAM is that the moment you find collision in this particular toolpath with the surface, move the toolpath towards the cut center. The cut center will lie somewhere here. Okay, basically it'll just find the most possible cut center, and it will start moving the toolpath inwards towards the cut center. Once it starts moving the cuts towards the cut center, you will realize that you'll get a very nice toolpath here, which is not doing any kind of collisions with the drive surface. And this is exactly what we get here. So if I look at the toolpath here, I get a pretty nice toolpath. Okay, so if I run the simulation of this part, let me go into the settings, see if I've switched on the material simulation. It's not. Okay, so we can directly go into the simulation here, go into the machine simulation, and I'll show you exactly how the machine would move like. Okay, so that's my tool, my part, the fixture, everything is mounted on the machine, including my toolpath. I can switch off the toolpath visibility and simply start the machining. Okay, it does very smoothly the entire machining. Okay, for our SolidCAM team members, I also told you that you could actually use this part. You could use this part for your exhibitions. We are making now a collection of these parts, which can be used for training your customers, also for using as a parts for your exhibition. Okay, so this is how we machined the top, and the same method was followed for machining the bottom. Okay, again, I did not come out of my machine simulation. I can just track the operations from my operation manager, and I can immediately start the simulation. So this is how we machined from the other side. In the collision check, we used a function called as automatic collision, automatic tilting when it finds a collision, so that I don't have to specify what exactly it has to do when it finds a collision. So it will automatically tilt the tool. It will either apply a tilt or a lead lag angle to stay away from colliding or creating collisions with the drive surface. Okay, so this part is completely finished. It's already there on the web for people who would like to download this finished part. And in the same method, we also did the finishing of the tube. We called it tube here. We also did the finishing using a 12mm lollipop tool. This is from the top side, and this is from the side. Okay, and then I created another small toolpath, which is called as an overlap, with a slightly different tool. Basically, the length of the tool was different along with the angle of the shank, and we created this overlap between the two toolpaths just in case some portion still remains unmachined. So we saw a completely different approach here, completely different tilting mechanisms used, different gouge check mechanisms that we used here. And to continue further, what I showed you was another part. In this case, it was the auto tilt in gouge check, especially when you have to machine. For example, you have to machine the surface. Now, it's not easy to machine the surface because when you look from top, the surface is already hidden by several other surfaces from the side. So here, we use the principle of auto tilt. So what we did here was I machined it as if we are going to go 100% normal to the surface, but in the gouge check, I used the tilt tool, and the strategy used was automatic. And how's my toolpath looking like if I run the simulation? This is how it looks like. The software will take into account all the surfaces that have been given for collision, and it will take into account that we need to avoid collisions with the surfaces, and it will tilt the tool accordingly. In some places, it is applying a combination of tilting and lead lag angle. Okay, so it generates a completely different kind of a motion there, and this is the auto tilt inside the gouge check. So it's a pretty useful function, especially for very tricky situations like the part that I showed you before and the part here. All right, Moving forward, I also touched upon another very important subject that we have here, and this is the toolpath conversion from 3-axis to 5-axis. So you have a simple 3-axis HSM toolpath, and why we needed that was we were using small tools, and if you look at the height that's there here, for example, if I take from that as the topmost point, and if I go here, you can see that approximately the height was 70 millimeters, and we had to use very small tools. So it was not possible for the small tool to have such a long height. So we use short tools, and we generate a 5-axis motion out of a 3-axis toolpath. And how does it behave? It's simple. As long as there is no collision between the tool or the holder, basically the holder, as long as there's no collision between the holder and the part, it's running like a 3-axis operation. The moment it finds a collision with the holder and the part surface, the part surface is tilted, or the part is tilted to avoid collision against the holder. So if I show you the converted tool path, this is how my converted tool path looks like. It's a simple 3-axis constant Z operation. So if I run this simulation, and if I go into my machine simulation, that's the part, and the tool, you can see it's a pretty short tool, and we have used the holder here. Let's run very fast, and because it's now simple 3-axis operation, like I told you that if there is no collision, then it starts with the 3-axis tool. The moment there is a collision, you will see that it will start rotating the part and tilting the part. Okay, you can see on the right hand side here where my cursor is moving, you can see the angles changing, and as it goes down, I'm just going to pull it down, and as it goes down, you can see that it starts tilting. So it's a pretty automatic operation. There's nothing that you need to define here. You just have to tell that that's my previous operation, and please convert this operation into a collision-free 5-axis operation, and SolidCAM will automatically convert it from 3-axis to 5-axis without you having to break any sweat. Now this is the same operation even if you would like to apply it for an operation like rest machining. So all these areas, for example, in this area, it's very clear that my tool cannot reach. So here it's tilting the tool completely. So if I show you here in the HostCAD simulation itself, okay, let's run. Let's go down into it. Okay, you can see that here it's avoiding the collision by tilting the tool. So if I reduce the speed further, this is how it's avoiding the collision. You can see that the holder and the part are quite far away and the tool is being tilted. And where there is no collision, it becomes a simple 3-axis operation. There's no change to the operation itself. Okay, so we also touched upon the very important area of converting a 3-axis toolpaths to 5-axis toolpaths, especially for mold makers who would like to utilize their 5-axis machines and reach those difficult to machine areas with small tools. From here, we moved on to another very important and nice subject of impeller machining. SolidCAM, by the way, directly has an impeller machining, so it's almost like a simple 3-axis machining. So let me open the part. Okay, so we have the part here. It's a complex impeller. It's not a simple impeller. You can see that. So what we need to do simply here is define your blade surfaces. For example, if you'd like to do the roughing, just define the blade surfaces, including the fillets and the splitter. Define your hub surface, You don't need to define everything. You just need to define one piece of the hub. Okay, it just needs to know where your hub is. And once that is done, define your tool, depth of cut, side step. And once that is done, ask it to generate the toolpath, and this is how my toolpath is generated. For many people, when I go and show this product to the customer or to an end user, they're very surprised. There don't seem to be any retracts in your toolpath, and that's how efficient the machining is of SolidCAM's impeller machining. There are hardly any retracts. You can see even the links, once it finishes this layer, are immediately joined there without doing any retracts. Okay, very safe and efficient machining for impellers. In this case, I used a 10 millimeter MOG taper ball nose, which has got an excellent, it can take a pretty big depth of cut. So I have given 10 millimeter depth of cut here. Since the tool is short, it cannot go all the way down. So we stopped the machining where it finished. And from there, we used another taper ball nose and we machined the remaining area with the larger or longer taper ball nose tool with a much finer corner radius and a very shallow taper angle. Okay, so this is roughing, straightforward. Select surface, select the hub, select the tool, select the depth of cut, enter the depth of cut, enter the side step, enter whether you would like to do one-way machining or bidirectional, and simply hit calculate. And the rest is done by SolidCAM. Of course, we only defined one portion of the surface. So what it basically did was it generated only this area of the toolpath, and then we apply the transformation to rotate it to the other areas. So it's pretty simple. So what we did here was roughing, and the same principle is applied also for finishing. Define your blades. Show this was my blade to machine, and the tool, and the depth of cut. That's it. Once that is done, this is how my toolpath is generated. I get my toolpath straightforward directly from the system. Right. We also applied, or the same technology is applied also to the splitter, and this is how my splitter toolpath is generated. I've used a bigger depth of cut here, but you can understand that for demo, this is pretty good enough. For a regular machining, of course, we'd go down with the depth of cut. We would reduce it. Right. And then once that was done, you can see that the fillets are not a constant fillets, they're variable. So it's obvious that we will have to finish also the fillets of the impeller. So we have got a specific function inside our impeller machining, which takes care of fillet machining. So we can have the splitter blade fillet finishing. You can see that we did exactly the splitter, nothing else. And it's going around only the fillets of the splitter to machine the splitters. And once this is done, we also applied the same technology to machine the main blade fillets. Okay, so within the multi-blade technology of SolidCAM, we have got roughing, we have got blade finishing, we have got fillet finishing, and we also have the final one, which is the hub finishing, where again we select the group of surface. So we select the group. This is the group of surface that we selected, and the hub, and this is how the hub is finished. Okay, you can see that simple. Group of surface, the hub surface to be defined, tool, the side step, that's it. The calculation is taken over by SolidCAM. Okay, these are all extremely safe toolpaths. They are already gouge checked, collision checked against all the possible surfaces. All possible scenarios are taken into account, and only then the toolpath is given out by SolidCAM. So a very important aspect is to in SolidCAM is the multi-blade machining. Right. Once that was done, we moved on also to our another area, which is another very important area here, and that was the tube machining or port machining. Okay, so SolidCAM has got an excellent application-based strategy to machine tubes and engine ports. For example, a port as complex as this one. So I'll just take a section Okay, so we have got a tube here with a bump, a kind of a bump surface in between with a fillet all around, and we can directly machine using either a ball nose tool or a lollipop cutter. We can directly machine by defining the surface. So all you need to define is the surface that constitutes the tube. And what SolidCAM will do is it will try to machine as much as possible. Again, let me go to my paint so I can explain to you much more clearly. Oops. Yeah. So what SolidCAM will do is this side, basically this side is considered as the top side. Okay, and this side here, this one is considered as the bottom side. Okay, so what SolidCAM will do is it will try and machine as much as possible from the top side. Okay, maybe it's possible only up to here, and then retract out, go here and machine the remaining from the bottom side. So you can specify whether you would like to go maximum from the top side or maximum from the bottom side, and it will machine accordingly. So by default, SolidCAM's machining is always maximum from the top and the remaining from the bottom. Simply by defining the surfaces, the tool, depth of cut, and side step, and of course, whether it's one way or bidirectional, you get this tool path. You can see very nice roughing tool path. No sweat, no need to define any kind of tool axis control or anything of that kind. You just need to define the surfaces, the tool, depth of cut, side step, and this is done. In the same way, we also can now machine the finishing area. Okay, you can apply a spiral finishing, and from the top it will machine as much as it can. It will go all the way up to here. Okay, all the way up to here, and the remaining one it'll just retract, go in and machine from the bottom side like what I indicated. So it's a very simple process, but for complex parts. It's not an easy part. Of course, this can be also be done using the generic machining. Like I showed you in the closed impeller, you need to define the kind of tilt curves that I've defined. Same thing applies even for this geometry here. Okay, so that's about port machining or the tube machining. We'll move forward. On the very first webinar, I showed you some interesting parts that can be done using what we call as a screw machining. Okay, so we have the basic screw or a simple extruder screw here like this. Okay, so we have a simple extruder screw. Even here, the machining is very simple. All you need to do is, if I go into my roughing, if I go into my roughing toolpath, all it needs is the target. It needs the machining area. Machining area here is not defined by a curve, but defined by 2 coordinates along the rotation axis. It needs to know what tool you're using. Basically, the tools supported here are bull nose, flattened mill, and ball nose. It needs to know your depth of cut, and it needs to know your side step along with the cut tolerance. And then whether it's zigzag or one way, you can define that. And once that is done, it will generate a very nice 4-axis roughing toolpath. Now, screw machining, for me, it's a bit misleading term, or it doesn't give you a right idea of what the software is capable of doing. So what I've done is, apart from this parts here, for example, this was the roughing, then we use the multi-axis constant step over here to do the finishing. You can see how neat the toolpath is. Okay, we have used the multi-axis constant step over here, and we also again multi-axis constant step over for this side, and multi-axis constant step over for the floor. You can look how we machined also the floor. Okay, using the parallel to curve strategy, and whatever was remaining here, okay, this area here, we did with the overlap finishing. Again, this was using the multi-axis constant step over. So we applied a simple method here of machining it, and this was done. But like I said, screw machining, the term is a bit misleading because it only tells the user that only screws can be done. But no, any part that is rotating around X or Y axis, which is a 4-axis operation, any part can be done using 4-axis screw machining. So to firm up that idea, I'll show you another part that was done. We did a simple, or not simple, I would say, a fairly complex, a fairly complex turbine blade. And the roughing of this was done using the screw machining principle. Okay, so I have this part, I have a stock, so I have my starting stock. Okay, not a weighted, sorry, the starting stock. So my stock was a rhomboid block. That's my starting stock. Based on the starting stock and the geometry that I defined, it generated a very nice roughing toolpath. Okay, so if I run the simulation here and go into my solid verify, you can see very quickly how it does the machining. In fact, as we speak, we have done a lot of improvements to this process here, so that the jumps that you see here are no longer appearing in the newer version of SolidCAM. A lot of things were worked out. You can see that you could just simply use any part that needs roughing, and you could use the screw machining to machine with screw machining and rough out that part using either a bull nose, a flattened mill, or a ball nose tool. Okay, let's quickly run the simulation. You can see the shape taking over. And this is completely a 4-axis operation. Okay, so it's not a 3-axis or a 3+1 operation. This is a 4-axis operation, and it takes into account the stock, takes into account the part, the tool geometry, and then just roughs out the part. All right, I'm now going to touch upon the subjects that you could not hear last time, and that is about the barrel tools. So I'll open a part. And I'll explain to you how it works inside SolidCAM. We use our generic machining, and with the generic machining, we can machine any part using all the circle end mills. So which are the circle end mills that we support? So we support, first of all, a barrel shape. We support oval form. We support lens form, and we support the barrel taper. So we support 4 tools at the moment. We will soon start supporting a tool which is called as a double barrel, which also is a combination basically of a lens form and an oval form. Okay, it will have both the profiles on the bottom as well as on the side. So we support these tools, and you can use these tools to generate tool paths on any surfaces that you like. Okay, for example, I would like to generate toolpath on the surface. Now, why do I need to use barrel tools? Okay, so let's open the tool first of all, and let me show the tool. Not this one, sorry. This is the barrel tool. This is the oval form tool. Okay, so this is my tool here. Let me zoom so that I can explain exactly how we work. Okay, so I will capture this. Okay, let me put that back. And why are we using this tool to machine the surface? Number one, this machine has got a pretty high curvature, or let's assume that it was even straight. To machine that surface effectively, we would need a pretty long tool, because if you look at the height of this part, the height is approximately about 194. So we are talking 190 millimeters. To get another flattened mill at this length is virtually impossible. And even if you get it, you would need to control the vibration of such a long tool coming out of the holder. So that would be an enormous task for the machinist. And another important thing is that, assuming that you don't want to use flattened mills and you would like to use ball nose tools, to get a scallop of even 2 to 3 microns on that surface would need a depth of cut or sidestep value of anywhere between 0.15 to 0.25, depending on the diameter of the tool you're using. So that would mean a lot of time spent in machining. And this is where the barrel tools or circle end mills come into play. All of these tools have got pretty large radius on the side, barrel end mills, oval form, or even taper. They've got pretty large radiuses. And we use these large radiuses to cut the surface. Now, the advantage with the large radius is that you can take the advantage of the large radius, take a very high step over, and yet achieve a very minimum amount of scallop on the surface. Okay, so what do we have inside SolidCAM group of tools when we use a barrel end mill? The most important thing here is the tool axis control. In the tool axis control, the moment you select either a ball nose tool or a barrel tool, circle end mills, you get a new tilt type, which is called as a contact point tilting. And in the contact point tilting, you have got the contact point definition, which takes into account the barrel section. So what I've said, I've defined two values here, 60 and 20. Let me go to my picture here and I will explain to you what I mean. The barrel section for me starts from this point here and it ends at this point here. Okay, so we consider the barrel starting point as 0% and the barrel end as 100%. So what I have told right now or to SolidCAM is that I have two starting points. One is 60 and the other one is 20. So I'm telling to SolidCAM, start at this point here, so 60, the 60%, and gradually move down your cutting air point till you come to 20%. So it will distribute the depth of cuts. For example, if my depth of the total height is 194 millimeters, that 194 millimeters will be distributed over this profile. So it will start here and it will end here. So the tilt that is needed is now being calculated automatically by SolidCAM based on the contact point it's making at every cut. Okay, so maybe the tilt here would be, let's say, 80 degrees. The tilt here could be probably 60 degrees. The tilt here would be 40 degrees and so on. So the tilt is calculated automatically by SolidCAM. Okay, so what I've done here is I've asked it to consider the barrel section and start my first contact of the tool with the part at 60% of the barrel profile or the large radius and end at 20% of the large radius. Now, because the part is too deep and I also have a surface below here, okay, let's take a section. Okay, I'll keep this section here. So I have got a surface here. It is not possible that it will touch 20%. It probably will stop at 28 because for making 20%, it needs to move the contact point to that particular area. For example, if I go again to my picture here, 28% probably will be somewhere here. Okay, in order for this contact point to be exactly on the surface, this much portion of the tool needs to be inside the surface. Now that would mean that it would create a collision with the surface. So it's actually going to stop much above, because in order to avoid the collision with the surface, the tool will stop. So it will not end up at 20%, but it will probably end up at 28% or 30%, depending on where the contact point is. So all I need to do is to define that. And what I've done here is I've defined the surface to be machined, okay, and the start curve, which is that, and my ending curve, which is that here. Once this is done, I have also taken into account the gouge check, and I'm trimming the collisions against all the check surfaces, bottom, side. It should stop, okay? And what I get here is this toolpath. So if I go again to the side, you can look at how the tilting takes place. The first one, you can see the first tilt happens at this point, which is nothing but the 60% what I'm talking about. So the first cut happens there, because what you're seeing right now in the toolpath is the tooltip representation, but the contact point is somewhere up there. So at 60%, that's where it starts the contact point. And as it moves down, now this tilt angle is automatically calculated based on the tilting point or the contact point it has generated. And as it moves down, okay, let's do that. And as it moves down, you can see that it's changing the tool contact point. So if I again go back to my picture, it will first start taking the first cut somewhere here. The second cut will be below that, and so on. And as it reaches down, my last cut would be probably somewhere here. This would be about, let's say, 28%. It won't reach all the way to 20%, but it will stop somewhere up there itself. Okay, so the tilt will be calculated automatically by, sorry, we have again some problem. Let's reload back. Now this was a much easier part. Okay, simple single surface. What we are now going to see is a slightly more complex scenario, a more real life scenario of handling of the barrel tool or the circle end mills. Let's open part. Now this is a completely different scenario. The scenario here is that you have got not just one surface, but group of surface. Okay, so I would like to machine this blisk using the oval form tool. Obviously, the advantage here is that I can have pretty large depth of cuts as against the ball nose tool, because of the ball nose tool, if I would like to have a pretty good surface, I just need to create a very small depth of cut. So what I have done here is, instead of using the from and to approach in barrel tools, like what we saw from 60 to 20, because here we have a problem with the space. I have got a problem of tilting, because if I start with 60 and if I say go to 20, we'll have a problem that it will start colliding against the next blade as it starts shifting its contact point. So here, instead of using a variable contact point, I have said a constant contact of 40%. Okay, take 40% of the barrel profile as a contact point and machine as much as possible. So what we get here is a very nice toolpath checked for collision using this here. So if I run the simulation here in HostCAD itself, this is how it will look like. So it's running the contact point exactly at 40%. So it's keeping the contact always at the 40% of the large barrel profile. And where we would need a depth of cut of approximately 0.15 to 0.2 with regular ball nose tools, here we are able to take a depth of cut of anywhere between 1 to 1.5 millimeter and yet achieve the scallop that is needed, or perhaps we would have got using the ball nose tool with a depth of cut of 0.15, 0.2. So the advantage here is faster machining, much better surface quality. Okay, but remember, very important, Barrel tools or circle end mills are tools used exclusively for finishing. You cannot use them for roughing. They cannot remove a large chunk of material basically because of their construction of geometry itself. So you have to be careful that you cannot apply barrel tools or circle end mill in every scenario or in every situation. Okay, they are not a solution for every surface. But of course, 60 to 70% of your paths can have areas where you can apply these tools. And SolidCAM will give you this possibility of applying these tools using the generic 5-axis functionality on any kind of surface. Okay, but remember, you cannot apply it in every situation, but you can find areas where this could be applied and apply using the generic 5-axis. So now what happens to the remaining area, because below this the tool has a limitation. Number one is a length limitation, number two is a tilt limitation, because we cannot go below this. If we go below this, it's going to collide against this blade. So SolidCAM has stopped the calculation here. Below that, you can use our regular machining using a taper ball nose end mill, and that's how you could machine using the taper ball nose cutters. Okay, very nicely done with the regular generic 5-axis. You can see the stark differences here, the depth of cut here versus the depth of cut here. Okay, and for people who would like to know that these particular blisks can be done simply using our generic 5-axis functions, including the roughing, if you already have SolidCAM's impeller machining, you can directly use the impeller machining, because impeller machining can also handle blisks for finishing and roughing, fillet finishing, everything. Or you could use the generic 5-axis functionality and generate the blisk roughing in this way. Here I've used a taper ball nose and generated the blisk roughing using the taper ball nose end mills. Right. We'll also touch upon another aspect or another area that we showed the other day, and that was the multi-axis roughing. And that was a part that we took, and I showed you two different approaches for machining using multi-axis roughing. It's pretty simple. If you have parts like this, you could do the roughing either 3+2. You would probably need 2 or 3 settings of 3+2, or you could use the multi-axis roughing straight away, where you define your wall, or rather your floor, and you also define your wall, the wall surface, including the floor. SolidCAM is pretty intelligent. It will exclude the floor surface and generate a 5-axis roughing toolpath straight away. So if you look at the simulation, if I go into the machine simulation, this is how it would look like. Okay, that's the part that's loaded on the machine. I've got my tool, and we start the roughing. That's the helical entry. That's the helical entry again. And this is how it will start machining it. You can see it's completely 5-axis. You can use ball nose tools, you can use bull nose tools, you can use flattened mills, you can use taper ball nose, you can use lollipop, you can use any kind of tool that you would like, and you can do the roughing and also the finishing of the walls and the floor using this method. Okay, this was one of the method. The other method, what we call is the adaptive method, and let me use that method and show you how we work with the method here. Let's say I have got this area here and I would like to use a flattened mill, bull nose solid carbide end mill, and I go full depth. Okay, I'll ramp, and it uses the adaptive method. And this is how the roughing works. Full depth of cut, use the full flute length and machine this part. Full 5-axis. Okay, very useful tool for machining areas similar to this. Okay, you can have different geometries also, but one of the geometries that you could do is the one that you're seeing on the screen right now. and looks very nice, very impressive, and it's very efficient also. Rather than running 3 or 4 different 3+2 toolpaths, you can just create it one using the multi-axis constant the multi-axis roughing, and machine the part totally. Right. Let's move forward. So these were the 2 areas that we touched upon last time. I'm going to move ahead with another important subject, and that's the multi-axis drilling. Let me open a part. Okay, so we have a part here, and I would like to do the drilling of all the holes. Now, it's not easy, okay, because you need to create different setups. Sometimes you can create setups, sometimes you cannot create setups. So multi-axis drilling comes handy here when you have got a large number of holes coming from different directions. Okay, so let's right click on the operations and go into multi-axis drilling. And in the multi-axis drilling, I simply jump onto the geometry and say new drill geometry. In the drill geometry, we have got to define the holes. Now, the holes can be defined automatically by SolidCAM. You can either use the auto function or you can use the manual function and select the holes. It will find the vector automatically. So in the auto function, we have got our filters. The filters are of 4 different types, whether you want to select through holes or blind holes or both. If you would like to specify a specific hole diameter, you can do that. If you'd like to specify a specific Z height or the height of the hole, you can specify that. Or if you have a color, because in many times in aerospace parts, they are defined by different colors. So you can specify a color of hole that you'd like to do the drilling. Okay. In this case, what I'm going to do is I'm going to use the hole diameter here and say, go from diameter 8 to diameter 12. Find all the holes. Okay. So I'll say OK, and I'll click on find holes. And within a click of a button, you can see that it generated all the holes that possibly lie between diameter 8 and diameter 12. You can see this diameter was not diameter 12 or 8. It's less than that, so it's wrong. It's not picked it up. Okay. Let's zoom here. We have got, because this is a complex scenario here. There's an intersection of 3 holes, so it has also picked one of the holes, which is not right. It's probably, I think it's the last group here. Yeah. No, that's not. Yeah, that's group number 11. Okay. So I will just remove the group number 11 from the hole. I don't want that. You can also select, for example, you can pick a hole and it'll highlight which group it belongs to. Okay, that's it. You can even reverse the vector in case sometimes the vector gets reversed because the part is an imported geometry, and in IGS sometimes you can have reversed normals. You can even reverse the vectors of the holes. So I will okay, let me pick hole and show you. So these are the holes that it has selected. Now it's doing a very random picking. You can also go and change the sequence, but what we will do now is run to the next level of selecting the tool. I'm going to use an 8mm drill here. Apply, and now this has got just, let's say, 35mm, and I've got a holder here attached to it. Some holes are pretty deep, okay, but I do not want to use this particular tool to machine 2 deep holes. So 35mm, I'll go to the levels. You can see the clearance is set to automatic. We will change this. We will go with a spear. In the spear, I'll say start with 250 radius. I don't want to measure it. I can do that. I can measure it and I can apply the exact one. And I'll say minus 225. Sorry. minus 225 is my center. Depth of the safety distance is approximately 10 millimeters. Technology, of course, I'm going to use drill cycle type G81, but I do not want my current post processor that I have here. We have got post processors that support cycles. We have post processors that also do not support cycles. So I do not want to use the cycle for this particular post, which I can do, or I can leave the post to handle it. And then I have got the sorting here. So right now it's default. Let's use the shortest distance and look how you can see this is how it has sorted it out. Okay, so it's using the shortest possible distance from one side and then applying it. You can change that method. You could go into advanced, and then you have got patterns here. You can select what pattern you would like. For example, I would like to use this pattern here. Say show sorted. This is how it looks like. So my shortest distance actually looks much more clean, and I'm going to use that method. Okay, tool axis control, it's 5-axis, and in gouge check I'm going to enable only the holder, and the holder will be checked against these surfaces here. I have got the check surfaces selection. So if I click on show, these are all the surfaces, the flat surfaces that are there. I've selected those surfaces as my collision check surfaces. Okay, and the method is to retract the tool till there is no collision, and I would like to keep 2 millimeter stop, or 2 millimeter away from the holder should not touch the surface. Okay, so this is done, and let's save it. We have got a traffic light, so we will synchronize it. So it's just re-recognizing everything. Okay, that's done. Let's right click on this and calculate. And this is my toolpath, straightforward, clean toolpath. Okay, so if I put this now onto the machine simulation, bear with me for 10 seconds for it to load. Okay, so that's the part loaded with the tool, everything, and we can start the simulation. This is how the simulation is going to look like. No collision. It's exactly doing what I've asked it to do. Tilted, and that's how it's going to machine it. The shortest path kicks in. You can see everything is done neatly and automatically with this function. So your holes can be in any direction. As long as they can be machined on a 5-axis machine, multi-axis drilling will handle it. Right. So that was about multi-axis drilling. We're now going to come to the towards our last chapter of the series of webinar, and that is that's a very important chapter, in fact, because many of my users, my colleagues, my customers are completely at sea when they come to this particular page here. So let's understand what this page is by taking a few examples. Of course, I'm going to touch both the pages. I'm going to touch on this page and also on this page. Okay, perfect. So before that, I would like to just open a part and get to my explanations. Going to open this part and I will get to the explanation. Okay, so just bear with me with this part. And I'm going to open a presentation and let's look at the presentation. So we have two subjects that we're going to look at, and that is the angle pairs and pole handling. Okay. In SolidCAM, in those last two tabs of SolidCAM 5-axis, you have got regular and advanced, and under regular you have got the angle pairs, and in the advanced you have got the pole handling. So in a 5-axis world of simulation, as well as for the real machine, provided your machine can do it, any point on the toolpath can generally be accessed in two ways. This is because of the vector, the tool axis orientation can be mapped as two different angle pairs. Okay, for example, let's look at this solution here. I have got the part that you just saw on the screen. That particular part has got a tool path and it can be machined using the first angle pair, wherein my tilt happens on the negative side or positive side. Okay, let's say this is the positive side and this is the negative. So the tilt here happens on the positive side. Also, the same point can be approached by rotating the C by 180 degrees and going on the negative side. So these are the two pairs of angles that are possible in any 5-axis CNC machine. Okay. Now, depending again on your limits, sometimes the point in a theoretical world can be approached using two different solutions, but in a practical world can only be approached using one solution. But we still have two angle pairs here, the first angle pair and the second angle pair. And then you have got a very small tip mark there called minimum angle change. Now, it's just not a simple checkbox, it's a very powerful checkbox. The minimum angle change parameter will force SolidCAM to select the angle pair, which will not create a large angle change from the previous toolpath. Okay, I will explain this to you. Okay, I hope there's nothing else. Yeah. Okay, so let's right now understand that the minimum angle change will force SolidCAM to select the angle pair that will not create a very large change of angle from the previous toolpath. Let's go to the next one. And then you have got another one called as a provide first rotation angle and provide second rotation angle. User can set this preferred angle for the first and second solution. SolidCAM will automatically choose the solution which brings the machine closer to the desired start angle. So if I have provided the first rotation angle as some angle, SolidCAM will find which solution among the first or the second angle pair is the right solution, which is closer to the angle that I've specified. Now it's a bit confusing, so I would like to explain it to you with the part itself. Okay, so I have got my first tool path here, and what do I have here? If I go into my machine control, I have not selected this option here, okay, minimum angle change, and I've set this as my first angle pair. So if I now go into my machine simulation, okay, let me go into the machine simulation quickly, and let's look at which side the tilt happens. So you can see that if I go into my right side view, it's tilted onto the negative side. What is the angle here? The B angle, or the rotation around Z, is set at 98 degrees and A angle is at -36. Remember this, okay? So this is my first angle pair. Now, I'll go to my second one, second toolpath, also doing the same thing. But instead of first angle pair, what do I have selected here is a second angle pair, okay? So if I now go into my simulation, by the way, this machine cannot tilt on the other side, so we'll get an error, but I would like to show you the difference. So when I say second angle pair, this is where it has gone. The B angle or rotation around C is -81, so it's almost 180 degrees that it has rotated. And the A angle, the tilt, has happened on the positive side, so it's +36. So these are the two angle pairs that are possible on a machine. Now, for example, this machine cannot go beyond +30, but there are machines that can do ±110. In those machines, it's possible that you can have two angle pairs, okay? So That was the first angle pair, and what you're seeing is the second angle pair, where the C-axis is rotated, or B in this case is rotated 180 degrees, and your A tilt is at positive. Now watch what happens here. My first toolpath was first angle pair, my second toolpath was second angle pair. But if I edit this toolpath here, okay, and if I select the minimum angle change, okay, just select the minimum angle change and calculate this toolpath. And if I go into my simulation, what happened? It moved, or it did not respect the second angle pair, because if it had to take it to the second angle pair, it would have created a large change in angle between the first toolpath. Remember, my first toolpath was the first angle pair. Although my second toolpath was second angle pair, it did not respect the second angle pair, because it would have made a large change in angle. It would have almost created a tilt, simply a tilt angle of almost 70 degrees. And not to mention the rotary would have done about 180 degrees. That's a pretty large change in angle. Imagine if this entire toolpath is post-processed and sent to the machine, this will retract and the entire table will tilt on the other side. So it's a big change in the angle. To avoid it, I selected that minimum angle change, and it kept the second toolpath also as a first angle pair. Okay, this is what exactly it does. Now, remember, my first toolpath was, the C angle was plus 98, and the A angle was minus 36. So I can go to my next option of providing the first rotation angle. So if I say provide my rotation angle, it was 98, right? Plus 98. So if I say my rotation angle is not plus 98 but minus 100 here, okay? And if I calculate this, where will it go? If I go to the simulation, I've said minus 100. Minus 100 is closer to minus 81. So it will tilt the tool to, or it will tilt, or it will use the second angle pair. But if I had put the same angle there, as instead of minus 100, if I had put plus 100, it would have taken the first angle pair, because plus 100 is closer to 98. Okay, so that's the whole idea of providing the first angle rotation or the second angle rotation. Right. There is another small tick here, is the machine limits. I think that's pretty clear what the machine limits does. Basically, machine limits will ensure that it will keep the machining within the limits of the machine. Now, if I say limit all, and if I put at second angle pair, okay, so if I again go back to my part, so if I go here, and if I say choose between solutions, second angle pair, and I don't use the minimum angle change, but I say limit, put the limit, and if I run the calculation here, it knows that this machine cannot do plus 30. Okay, so let's see what it does now. It took the tilt to the first angle pair. Although I've selected second angle pair, although my minimum angle change is switched off, I said respect the limits of the machine. So the moment I do that, it takes it into the first angle pair. It automatically goes into the possible angles that's possible on that particular machine for that particular toolpath, right? So that's about the limits. Let's go into the contentious area of pole handling or singularity in 5-axis. Okay, for many people it's still a mystery. It's a mystery box. It was also a mystery box for me for a pretty long time till I figured out what it is. But trust me, it's not as simple as it looks like. It's a pretty complex area. Now, first of all, we need to understand what is a singularity or what is a pole. Singularity or a pole is a situation when the rotary axis vector is parallel to the tool axis. In this case, my rotary axis, that is the C-axis here, the table that is rotating, the vector of that is when it becomes parallel to my tool axis, That is what we call as a singularity or the pole. The moment it comes into a singularity situation, anything is possible, because then you get a lot of solutions. The machine can behave, or the software can behave, or it can get too many solutions. So you need to restrict on what the software can do and what the software cannot do when it comes into the situation of singularity. So what are the options here? We have got several options. First of all, we have got in the singularity, we have got freeze around pole. We have got use rotation angle around pole to stay within the linear limits. Then we have linear interpolation of the rotation angle, smooth interpolation of the rotation angle, and force stable rotation. So these are the 5 options that we have to handle pole, or the pole situation, or the singularity situation. The first one, SolidCAM will convert the rotation axis into linear axis and machine the part like 3-axis. Okay. So if you select freeze around pole, the moment in 5-axis it comes to a situation where your C-axis or rotation axis is parallel to the tool-axis vector, it will behave exactly like this. You can watch this video. It will just machine it exactly like 3-axis. Okay, although it was a 5-axis toolpath, but because it has come into a singularity situation, it will machine it like a 3-axis part. The next situation is use rotation axis around pole to stay within the linear axis. Very interesting. As long as it is not violating the linear limits of the machine, X and Y limits of the machine, it will behave like a 3-axis toolpath. Okay, so on the left-hand side, it's not violating the linear limits. Okay, it's within the limits of the X and Y axis of the machine. So it will now generate a simple 3-axis toolpath, or it will behave like a 3-axis toolpath. But the moment, let's say the part was big enough and it was exactly fitting and violating a little bit of the linear axis, this is what happens. The moment it violates the linear axis, it will keep the tool stationary and it will rotate the part around it. Okay, so you can now understand what the singularity is, or a pole is. So you can get so many situations. Let's move ahead. Linear interpolation of rotation axis around the pole, as well as a smooth interpolation. They're both very similar. There's hardly anything to be taken out. In the linear interpolation of the rotation axis, the rotation axis transition has a constant speed. That means it just knows that it needs to move from point A to point B, and it'll just use point A to point B as a feed rate, and it'll move as if it's going in a linear axis or constant speed. But when it's doing a smooth interpolation, sorry, yeah, this is a linear. It's still not attained the pole. The moment it comes into a situation of the pole, when it's parallel, you can see it changes, or it rotates the part in such a way that it needs to respect the limits of the machine, because this machine can do only on one side. So it will rotate the part, and that rotation speed is constant when you select the linear interpolation. In the smooth interpolation of the rotation angle around the pole, it's exactly similar to linear interpolation. However, the transition will have an acceleration and deceleration of the rotation axis. Okay, so it's pretty much smooth when compared to linear. You can see it did not rotate completely fast or very quickly. It rotated very smoothly to go into that point. Okay, this is the difference between the two methods. Okay, again, smooth traversing over to another point. Okay, And then we come to the tool repositioning, and I would like to show this on the example. Okay, so let's open another part. Let's open. Do I have it here? Let's open it from the directory. The singularity. So I have got this simple part. It's a spear, and it's exactly not a spear. I've got a straight portion on top to explain to you the difference between all these three things. What we have to look here is the smooth interpolation. So let's run the simulation and go into the machine simulation. What I've done here is I've placed the part on the corner so that it's much more easier to understand the interpolation. So let me look at the toolpath. Let's go slowly. So here what you can see is it's finished, and that's it's rotating completely in one. And that's happening because, like I told you, that minimum angle change parameter, it's not a very simple checkbox. It's slightly complex checkbox. If I go into my machine control, if I select this option, this is what it will handle. Okay, so if I go into the linear interpolation now, and if I run the simulation, okay, that's my toolpath. Let's run it, and you can see that it immediately rotates because now the rotation angle is more than 180 degrees. It has rotated and it comes back here and to machine this side. Okay, so it's just one block, linear. Okay, from point A to point B, just one block, so it rotates 180 degrees. Now, which parameter is that is making it go up? So if I go into the analysis here and look at the tool number, you can see that I have got a retract in the center. Now, this retract is caused by this parameter here. The retract is caused by this parameter here, the angle change. What I've said here is if the angle change is more than 30 degrees, this tool needs to retract 100 millimeters up and allow the part to reposition and then come down again. Okay, now the same situation we can avoid by adding points, not allowing point A to point B, but putting points also in between on that flat area. So what I've done here is I have put a spacing between 2 points. And if I now look at this simulation here, earlier you would get point A and point B from that flat area. But if you now look, because I've used the point spacing here, if I zoom into that area, so that's my flat area here. And if I look at the toolpath rendering and go into the toolpath points, you can see approximately 19 points that it has put on this. So there are no jumps. So if I go into the simulation, it will comfortably rotate and go to the other area. No retraction happens now because now I have put points. So the angle change, so if I move here, the angle change is happening gradually. Okay, you can look at here, 0 from 90, 86, 82, 82, 74, 65, 55, 45, 34, 23, 11. That is because there are linear points on the profile, on the surface. Now, because each linear point will be mapped to an angle, so it will now divide that 180 degrees by 18 points, and so that's the reason you're seeing the difference between two angles as 10 degrees. So it will map that angle against the point and rotate the part. Right, now let's look at what freeze around pole looks like. So this is a 5-axis toolpath. Okay, now let's look at some fun. I've used tool axis control as 90, so it's going to be this, the flank of the tool is going to cut. And if I go into my machine control, I have set freeze around pole, and if I run the simulation here, machine simulation, so I've got tool, and you'll see it's simply going to do a simple 3-axis movement. That's it. No 5-axis, although it was a 5-axis toolpath. However, let's trick it a bit. Okay, I will say instead of 90 minus 90, I have got minus 89.998. Okay, remember the value 998. Let's calculate this toolpath and let's see what happens now. Okay, let's run the simulation. Go to machine simulation. Okay, same. Let's run slowly. Difference change in angle. It's jumping around because the change in angle is much more than what was anticipated by the software. Okay, so the freeze around pole works very well when you have straight flank cutting. So if there is no change, no limit violation, it's going to be a simple 3-axis solution. So let's save, calculate this, let's come out, and then we go into retracts. So I'm going to run the simulation. It's a simple 5-axis toolpath. I'll go to the machine simulation now. That's the toolpath. Let me switch off the points and let's run the simulation. Simple 5-axis toolpath, and you can see it's continuously wrapping around till it reaches the end. Okay, now let's assume this machine had a limit, and that limit I specify in my machine limits, my C table. I'll say it goes only from 0 to 360. This is the limit. Save it, go out. Okay, and what I do simply here is I edit the toolpath, and in my machine control, okay, I've got this angle 30 degree, and my retract distance is 100. It's just basically the same toolpath. Okay, and the angle value between two angles is 10 degrees. So change in angle is not more than 10 degrees. If I run the simulation now, remember I've put the limits there from 0 to 360. The toolpath now looks very nice, okay? But this is not the actual toolpath, okay? This is only the toolpath representation of what it was in the software. But what it's going to look like on the machine, I need to go into the analysis and go into the tool number. This is what is my actual toolpath. After every 360-degree movement, the tool retracts 100 millimeters. There's a rewind of the C-axis, and the tool comes down. So actually, this is how my toolpath is not going to go, rather it's going to look like. So if I run the simulation, let's go into the move list and keep an eye on the C-axis rotation here. 360 degrees, rewind, down. 360 degrees, rewind, and down. So that particular box does this functionality for us. It retracts, rewinds, and brings back. Now, when it does the rewind, you can see that when it's doing the rewind, you can see that I've specified the change in angle to be at 10 degrees. So the rewind starts at 360, 350, 340, 330, 320, so on, 10 degrees till it reaches to 0. And in 0, it comes down again and starts the machining. Okay, and you can specify whether it's 100 millimeter or more. Okay, right. Let's look at, let me delete this last one, I don't need it. Let's look at the value here. So I'm not going to go back to my machine, and I'll change the values here to minus 999 and plus 99. Okay, let's save it. So I have got again here my toolpath, the same toolpath using the flank. And if I go into my machine control, I've set use rotation angle around pole to stay within the linear limits. Okay, perfect. So let's now run the simulation. Let's go into the machine simulation and see what it looks like. Okay, so that's the toolpath, the tool. If I run the simulation, it's a simple 3-axis. It has done nothing. Why? Because it's not violated any of the linear limits. Okay, now I'm going to make some changes to my machine, and I'm going to make the toolpath violate my limits, right? So double click, I'll go to my y-axis and I'll say minus 75 to plus 75 is my limit. X-axis, minus 75 to plus 75 is my limit. Let's save. Go here, change some parameter basically to make it recalculate again, maybe the tolerance. Okay, let's hit save and calculate button. Okay, let's go into the simulation. Let's run the machine simulation. Okay, let's see now what happens, because now it has violated the limits. Let's run the simulation slowly. You can see the moment it violated, there is no longer 3-axis motion. Only the C-axis table is rotating and the tool is turning. Okay, very important. You can use those tricks to machine large parts on machines where they are exactly fitting and you have a corner where the tool actually can go. Okay, it will just go into that, it will dip into that area and machine it without violating your limits. Okay, so you can use the singularity to your advantage rather than your disadvantage. You can use the singularity to your advantage and machine the parts the way you would like to machine them. Right, so I've touched upon totally 11 topics today. Some things that were done in the last webinars also I've touched. Some things that were not done in the last webinars also I've touched upon. A slightly lengthy webinar today, about 1 hour 45 minutes roughly. We are done for the session. If there are questions, I'll be more than glad to answer your questions. I believe there are some questions. Yes, somebody asked me for the parts for training. You can get it for sure. I'm going to put all the parts that you saw today, all the 11 examples. There'll be more, in fact, not 11. There'll be at least 13, 14 examples that we have. You're going to get all those examples on the web. It'll be there as a part of the recording, and you will enjoy it. If there are questions, you can always reach me. You know where to reach me, or either on Skype or on my email, amod.onkar@solidcam.com. You can reach me on the email address, and I'll be more than happy to answer your questions. If you have got parts that you're stuck with, please send me those parts. I'll be more than happy to address those parts. Remember, we are stuck at our homes for the next 3 weeks, so this is the best time to send me the parts, and I'll be more than glad to help you around. If there are no more questions, I would like to really thank you very much for attending this webinar, and I only hope and pray that you stay safe, Stay inside your homes, and this too shall pass. Thank you very much for attending this webinar. See you. Bye-bye.